Okay, as I said, most people try to fit this into the formula that you have, and a lot of you remember the formula, and that's good. But I really don't like that formula very much because you use the formula to bypass understanding compound interest. Okay? Now, you can answer this question without the formula. Now, when you get down to here, the formula might be handy, but you don't really need it. I'm going to show you why. What does it mean to compound at 100% interest for 6 months? Okay? How much interest are you going to get after 6 months? When I phrased the question, I said, okay, well, you're getting 100 interest for a year, 100% interest per year. How much do you get for 6 months? And everybody pretty much thought, okay, yeah, 50%. Yeah, that's what it means to compound. You split your interest up so many times, and then that many times a year, you get to apply that interest. You get more money that way, as you're going to see. So 6 months, interest will be 50% of 10K or 5K. You'll have 10K plus 5K equals 15K. Okay. Then how much do you have after a year? You get another 5K? No, you get more than that. Your next 50% applies to the 15K. Good, it'll be 15% of the 15K. 2% is half, that's 7.5K. So you'll have 22.5K. Simple interest. Would only give you 20K. Now, if you do simple interest for a year, that means you take 100% of your 10K, that's your interest, it's another 10K. Add that to your 10K, you get 20K. Okay? So what compound interest does is every time you compound on your new amount, which gives you more interest. Make sense? So we could look at this. Okay. Here are your principles: 0, 1/2, 1, 1.5, 2. Okay, the other thing is adding future percent the same as multiplying by 1 plus 1.00 over 2. $1.50. Okay, so in year 0, your principal is 10K. But year 1/2, it's 10K times 1 plus 1.00 over 2. That's basically what this calculation was. Okay. Now, this is common sense statement. This is equivalent statement in a little more mathematical language. What does it mean to do 10K times 1 plus 1.00 over 2? Well, 1.00 over 2 is 0.5, right? And that's going to be multiplied by the 10K. That's a distributive law, right? So multiplying the 10K by this is your interest. That's $500, $5,000, 5K. Okay. Multiplying 10K by 1, well, that means you get to keep your 10K, which is the way interest works. So you have your 10,000 from this, and you have another 5,000 from this. So this is how you add 50%. You multiply by 1 plus 1.00 divided by 2. The next something. You multiply this by 1.00 over 2, so you're multiplying by 1.00 over 2 squared to get this amount. And if you do that, you're going to find that you end up with your 22.5K. Then 10K times 1 plus 1.00 over 2. Well, you multiply by that factor again. We started with 10K times this factor squared. You multiply by that same factor, and you're going to end up cubed. And pretty soon it gets pretty monotonous. Power is going to be 2 times the number of years. And that's where the formula comes from. Now, I developed that in a lot of detail in the MDE class. But you understand that in this example, you just say, if I'm compounding twice a year, that means I get 50% every 6 months, right? If I'm compounding quarterly, what would I get? What's quarterly mean? It means 4 times a year. I get 1/4 of that 100%, 25% after 3 months. Another 25% on that principal after another 3 months. Another 25% on that after another 3 months, and so forth. Now I'm going to summarize rather quickly what we did in the MDE class. Support class.
Like not like to do that. It looks like you feel right.
Started off 100% annual interest on $1,000, and we're going to compound it 10 times. So what percent interest do we get? Every time we compound? Show me your fingers. 100% being compounded 10 times. Gonna get 10%, right? Everybody's waving at me with two hands. Okay. You end up with $1,000 times 1/10 of 10%, 10 times. That's what this means. If you use a formula without understanding what it means, you don't understand what's going on. Okay? Which is pretty much what open math taught you to do. Okay? So if that's all you did, that's all I would expect that you did. But I want you to go a little step further and understand what's really going on. So that after 1/10 of a year, you get to add 10%, you'd have $100 interest, you'd have $1,100. Then you take 10% of that and add it. You get to add $121 the next time, and so forth. I want to go back to page here, it's just a little bit, same thing. This is annual interest. How much do we have after each year? Okay. Each year, we get to add the full amount we started with. Now, I say that's going to be $1,000 plus 100% of $1,000. You know, 100% is 1.00. So 100% of $1,000. Okay. I write that as $1,000 times 1 plus 1.00 to indicate you keep your interest and then you add 100%. And of course, that equals $1,000 times 2.00 or $2,000. After 2 years, what do you have? Well, it turns out you take your $2,000. $2,000 times 1, that's your original $2,000. $2,000 times 1.00 is 100% of $2,000. You add that and you get $2,000 times 2, which is $4,000. Now you can figure out these numbers without writing it like this, but to understand how the formula is built up and to understand how compound interest works, you want to understand how this is written. So that we then could list year 1, 2, 0, 1, 2, 3. Formula here. After 2 years, we take this amount here and multiply it by 1 plus 1.00, which makes square. Third year, we take this amount and multiply it by the same factor, so that now we have 1,000 times 1 plus 1.00 cubed. So now we can extrapolate. 10th year, how much do we have? 1,000 times 1 plus 1.00 to the 10th. Okay. After 2 years, it's going to be 1,000 times 1 plus 1.00 to the t. Now, ultimately, I go ahead and add that 1 to the 1.00. I want to keep it separate because I want to understand what this means and what this means. But when we finally get the formula, we have $1,000 times 2.00 to the t. We build this up. And if you don't understand that, seeing it right now, go back and look at those videos. Okay. So we have 1,000%, $1,000 at 100% annual interest. We get $1,000 times 2 to the t. How do you graph $1,000 times 2 to the t? You construct your exponential graph because this is nothing but a vertically stretched 2 to the x graph or a 2 to the t graph. It's your toolkit exponential function. You can construct that graph you put the red dot on it. Your lowest line above the lower edge stands for y equals 1,000, because that's where your principal is $1,000. You move over 1 year and you got $2,000. Move over another year, it doubles again to 4,000. Move over 1 year, you have 8,000. One more year, you got $16,000. So all this holds together. If you compound quarterly at an annual 100% interest, how does that change? Well, 25% every compounding. And you do that 4 times per year. It means you add 25%, 100% over 4 times per year. And that's the same as multiplying by 1 plus 0.25 4 times a year. So what's your result? You start with $1,000. After a quarter of a year, 3 months, you have 1,000 times 1 plus 0.25. Again, that means 1,000 times 1 is your $1,000 that you get to keep. 1,000 times 0.25 is the 25% you get to add. After half a year, you take this amount and multiply by 1 plus 0.25. So you got 1,000 times 1 plus 0.25 squared. I didn't write it out for the third quarter, but you would take this and multiply it by 1 plus 0.25, and you'd end up with 1,000 times 1 plus 0.25 cubed. And at the end of the year, you'd have 1,000, and you'd have done the 1 plus 0.25 4 times. Multiplying it by that factor each time gives you 1 plus 0.25 to the 4th. That comes out about $2,500. At this point, we can say that your effective interest is $1,500. You started with 1,000, you've got 2,500, you've added $1,500. Okay. And that's 150% of 1,000, isn't it? So your effective interest is 150%. I give you 100% interest, and if you can find somebody to do that in a safe investment, by all means do it quickly. Okay. But if I give you 100% interest and offer to compound it 4 times a year, I'm effectively giving you 150% interest. Okay. And it gets better than that. What if I compound it 10 times a year? That's what I started to do. Think. Right here. This time, instead of multiplying by 1 plus 1.00 divided by 2 or divided by 4, I divide it by 10, and I do it 10 times in a year. Okay. So if you compound this 10 times, you end up with multiplication by this thing 10 times, which gives you the 10th power. And there is what you have. That would be, and this says adding 1/10 of your 100%. That's the arrow here. There's your 10th of 100%. 10 times. There's your 10 times. Okay. You can multiply that up, and you end up with something like $2,600. Okay. Now let's think about it now. If you compound it twice, you end up with $2,250. If you compound it 4 times, you end up with something close to $2,500. Okay. So you jump from 2,000 to 2,250, and then from 2,250 to 2,500, you got pretty much equal jumps. So you think it's going to keep jumping like this. You just keep compounding, compound it 1,000,000 times, and pretty soon you're alone in the universe. It doesn't work that way, but seems like it might at this point. But okay, we observe now, if we compound 10 times, we go from 4 times to 10 times. We go from having $2,500, which is what we got for 4 compoundings, to about $2,600. Now that only jumps $100. 4 is jumping like $250. Okay. So if we compound weekly, that's 52 times. How would we do that? Well, we just divide our 100% by 52 and multiply by this factor 52 times, which is the same raising it to the 52nd power. And we go from 2,600 to about 2,690. Okay. If we compound 1,000 times, here's what we get. It's 2717. Now, 2,690 to 2,717 is only a $27 jump. That's from compounding it 52 times a year to compounding it 1,000 times a year. It isn't changing by much. So you could say, okay, what if I compounded 1,000,000 times? What if I compounded 1,000,000,000 times? Well, you could do this, divide by 1,000,000 and raise it to the millionth power and put that in your calculator. You'd come up pretty much with 2718 or 2719. You will never get 2719 though. Okay. So as you increase your number of compoundings, your result goes up pretty fast at first, but then it starts to level off. Okay, maybe exponentially, maybe not. Okay, there's a limit. And what we say is, okay, this expression, if n is your number of compoundings, so instead of compounding it 10 times, you compound it n times, what would the expression be? Well, you're going to divide your 100% by n, and you're going to raise that to the nth power. Okay? And that's what we do here. That's just this expression where we use n for the number of times we compound it in the number of compoundings. We get this. Limiting value of this number as n approaches infinity is that number e. That use e to the x. Okay? It's approximately 2.718281828. It doesn't repeat. Just looks like it's going. It's a coincidence of the number system. Then, if we compound continuously, which means every instant, that's what this corresponds to. We let the number of compoundings approach infinity, which means the time between them approaches zero, okay? And in the limit, we're compounding continuously, and the principal would be $1,000 times e to the RT, where the rate is now R. No longer 100%, rate is R. Now, in these examples, if the rate is R, then we would use R here instead of 1.00. And there's the formula you have in the book, but there's the meaning of the formula. And I want you to be able to explain how quarterly compounding works without using the formula. Okay? You just split your interest into 4 parts and apply it 4 times. Okay. Then there's a statement here. It says in general, for continuous compounding, P of t equals P naught e to the RT, where P naught is your t equals 0 quantity. Could be your principal of an investment. It could be a population. Could be something else. Something that grows exponentially. Okay. That's compounding continuously. If you're compounding n times, well, you just divide your interest rate by n. That's what you get for one compounding. And then you do it n times for every year. Okay. So if you're compounding it n times a year for t years, you're going to have to multiply by this number n times t times. Then I say that the continuous growth of anything at a constant annual rate R. There you have it again. We do somewhere. Example. And here's the example that we started with. In the year 2030, we have $600,000. The year 2035, we have 750,000. Question, what can we figure out from this? Well, as soon as you have data like this, I hope that you're conditioned to put it on a graph. Okay, so like in 2030, your portfolio is worth $600,000. That'd be nice. Okay, in 2035, it's $750,000. Okay. Now, it could be in 2030, a loaf of bread costs $100,000, so you don't have that much. But I don't think we're on track for that. Okay. If we assume continuous growth at constant rate, well, first of all, we put our information on a graph. It's going to give us 2 points on the graph, right? Here's 2035, and I'm going to call that t equals 5, and I'll let t equal 0 in 2025. That's like today, okay? Right now it's 2025. If t equals 0 in 2025, t is 5 in 2030. That makes sense? And it's 10 in 2035. We put these 2 points on the graph. Where's this point? That point goes with t equals 5 and p equals 600,000. This point goes with p equals 750,000 and t equals 10. So we have 2 points on the graph, and then I sketch what might be an exponential curve. I don't claim that it's a really good exponential curve, but it kind of looks like it. Okay, just to represent what's going on. And now we're going to figure out what the P of T is. Now, you had a problem in your homework where you're given 2 points in an exponential graph and you're asked to find the function, right? Remember that problem? Somewhere around problem 7 or something like that on the homework. Okay. So we're going to do something very similar. The first point on our graph tells us that P of T is 600,000. Okay, when T equals 5. So we take 600,000 and 5 and plug it into the equation. What's the 600,000? That's the P of T. What's the 5? Well, that's your T. So instead of P of T equals P naught times B to the T, P of T is 600,000. So we write 600,000. And that equals P naught times B. T is 5. Replace this by 600,000, replace T by 5, we get this equation. Then from the second point, we replace P of T by 750,000 and T by 10. And we get this equation. You probably can't read very well, but I wrote them up here again. Okay. So from these 2 points on the graph, we get these 2 equations. All we got to do is solve them. Now, you're going to have to solve a lot of simultaneous equations between now and the end of the course. You've already learned how to do it for a linear function. Use y equals mx plus b. You got 2 points. Put the x and the y for 1 point. You got an equation. Put the x and y for another point. You get an equation. And you can solve for m and b. You need to be able to do that. And people did that fairly well when it occurred on midterm and major quiz, but not everybody did it well every time. So you want to be sure you know how to do that. Okay, well, in this case, the equations are a little different. It's not y equals mx plus b. It's a different kind of an equation. So how do we solve this system? Well, we can solve for P naught. We have to solve. What do we have to solve for? The only things we don't know in this equation are the values of P naught and B, right? It's two parameters. We have two equations. We should be able to solve it. Okay. To solve this, I pick on the first equation and solve it for P naught. Well, that's really easy. To solve this equation for P naught, we just divide both sides by b to the 10th, right? And that gives us I don't know why I'm pointing to this equation. This is the first equation. We're solving this equation for P naught. So we have the first equation is P naught b to the 5th equals 600,000. How are you going to solve that? You're going to divide both sides by b to the 5th. Then b to the 5th over b to the 5th is 1. That just leaves you P naught equals 600,000 over b to the 5th. And then we plug that in to P naught here. So this 600,000 over b to the 5th is going to go here, and the equation is going to look like this. Here's our b to the 10th. Here's our 750,000, and our P naught has been replaced by this. That equation is easy to solve for B if you know your rules. Okay. So b to the 10th divided by b to the 5th is what? It's just b to the 5th. If you don't know the rules of exponents, it's on you. Review them. Okay, don't be making mistakes with the rules of exponents. And that was pretty fundamental. Okay, so you're dividing, you subtract the exponents. Well, that's getting there. We've only got b to solve for. What's the next thing we're going to do? Well, we don't want that 600,000 confusing things on this side, so we divide both sides by 600,000. So here, 600,000 divided by 600,000 is 1, so we just end up with b to the 5th. 750,000 over 600,000 is 1.25. We have b to the 5th is 1.25. Then how do we solve that for b? Well, there's where people, pretty good with the laws of exponents here, but this can give them a little bit of trouble. We do b to the 5th to the 1/5. Why? Because when we do a power of a power, we multiply the two powers. It's one of our basic rules of exponents, and it's very important in this chapter. Okay, so be sure you understand how that works. Anyhow, that's going to give us b to the 1, which is just b. So now we solve for b. All we got to do is evaluate 1.25 to the 1/5. Well, you plug that into your calculator. Make sure you put parentheses around that 1/5. Okay. Something I would hope you learned a long time ago, but I see people making that mistake. You just put in 1.25, put the exponential, press the exponent button, then put parentheses around 1/5. Okay. And you're going to get 1.046. Now, what good is 1.046? Well, it's 1 plus 0.046. Okay. We've seen expressions like that, like 1 plus 0.25, which we raise to the whatever power. 1 is the population that you get to keep, and 4.6% is the rate at which it grows. Okay? Make sense? So this is telling you that your money is growing at an average of about 4.6% between 2030 and 2035. Okay? Kind of worth knowing. Worth being able to think about these things and understand what the calculations mean, as opposed to blindly following complicated formulas. That really aren't that complicated if you understand what's going on. So I'm just advocating, understand what's going on. I can't imagine that the world has progressed to the point where we're giving people formulas for compound interest in a pre-calculus class. That belongs in a freshman finance class in high school. Okay, it's not pre-calculus. Now, that is a good example of exponential functions. And if you're not trying to really understand exponential functions, or if you're trying to understand it from a different perspective, yeah, maybe it's okay. But I think we're just dumbing it down, okay? Now, the other thing, we've got our effective interest rate or growth rate, okay? We still have to find P naught if we want to extend this model, if we want to find out, okay, what should we have in 2050? Okay. In 2050, y'all are gonna be that old. Okay. Gonna need this entire formula. And you're gonna need to know what P naught is. You know what B is, so you just put in 25, because T 0 in 2025, it's 25 in 2050. We gotta figure out P naught. Well, it turns out that that's easy. We've already said that P naught is 600,000 over B to the fifth, right? Well, so P naught is 600,000 over B to the fifth. We already found that out. We've now found B, so we just put B back here, and we find out that P naught is 480,000. Okay. So somebody who has 480,000 right now gets approximate 4.6% interest. If that lasts for another 10 years, those are going to be the amounts. Does that make sense? It should, because you've done a lot of calculations with the formula, you know how it works out. And you've had at least one problem that asks you to solve the simultaneous equations. Hopefully you did that. And incidentally, in the homework, and I ended up spending a fair amount of time, but about 3 times the usual time, putting comments into your homework and figuring out what you were doing on the homework. On the stuff you submitted, I couldn't, in many cases, see the steps that you use in solving the problems. I can't help you much if I can't see the steps. Sometimes it's obvious from your answer what you were thinking, but if you're not showing me the steps, I can't really put a useful comment into your homework. Also, next time I teach this course, if I'm not seeing the steps, you ain't getting that 5 points. You might get 2, okay? I'm not gonna do that now. I just want you to do it. Try to give me as much information as you can when you do. Also try to organize things a little bit. I don't even know what problem number I just see a bunch of scratchings and they all make sense. Okay, there's 5 points. That's good enough, but you're not giving me the information I need to help you. If I'm looking for what you did in problem 11, I don't want to look at 6 pages of disorganized random scratchings. Somewhere in those disorganized scratchings, there ought to be an 11 and a big circle around the 11 stuff. Then I can handle it. And if it's more organized than that, that's even easier. Okay. But yeah, I could handle that latter. I can't handle a bunch of mixed up numbers. 6 problems in one jumble. I can't sort it out. I'm not gonna take time to sort it out, okay? So I kind of take that as a lesson because it hopefully give you a lot of help here in the last part of the course. Another comment. If there were 600,000 fish in the lake in 2030, 750,000 fish in 2035, you would get exactly the same model because those numbers are exactly the same as these numbers, right? But now it's a different model. It's a different meaning. Okay? It's, what rate are the fish reproducing? Okay? That's your 0.046. Fish population goes up 4.6% per year. And if you want to know how many fish there were way back in 2025, if it's 10 years hence and you have this data, you can extrapolate back and say there must have been about 480,000. Plus some change. Okay.
We've seen kind of video. This is something that or downward call. Is that like that data and but that
Log base b to the t function is the inverse function of y equals b to the t. So for example, and I'll use x instead of t. Right here is your table for y to the x. Your table for y equals log 2 of x. I can construct the y equal 2 to the t shape and put coordinate axes on it and so forth. If I want to do the inverse function, I reverse the coordinates of all these points. So this point is 2, 4. Let me work out the details, but I get the point 4, 2. This point is 1, 1, out, 1, 2. I get the point 2, 1. This point is 0, 1. I get the point 1, 0. This point is -1, 1/2. I get the point 1/2, -1. And then the point 1/4, -2. Open Math will explain this fairly well. So if you got the graph of 2 to the x, and I've been using x, b. Get the graph of log base 2 of x. If you got a table for 2 to the x, you can reverse things and get a table for log base 2 of x. That's equivalent to y equals b to the x. Now, I'm going to write this equivalence a little bit differently. I'm going to give you a rule that says, okay,
Reality or log?
log base b of c equals a is equivalent to b to the a equals c. Okay? So this expression here, or equation, log base 2x minus 3 equals 10. Is this expression in this form or this form? Well, pretty obvious, got that LOG in there. It's in this form, right? So for this expression, then in this expression, if it's in this form, what's A, what's B, and what's C? Let's write that out. Okay, now this is very simple. If you remember this rule, which just comes from the fact that the log is the inverse of the exponential function. This is your basic premise, and this follows from the premise very quickly, okay? And this is a form you'll often use it in. If you have a logarithmic equation like this, where the x is bound up inside the log, you can rewrite it as an exponential equation and solve. Just add 3 to both sides and divide by 2. Okay? You get 1,027 over 2, which is 513 and a half. Of course, everybody saw that. Immediately did that in their heads. Okay? Now, that's an easy equation to solve. I'm going to give you a couple of other equations. And you're going to use this to interpret them. Okay, so first equation I'll give you is e to the x minus 3 equals 2. I'm not going to do e. I'm going to do to the x minus 3 equals 2. Now, which form is that in? Give me a thumbs up or a thumbs down. Thumbs up for this form, thumbs down for this form. It's in this form. It's something raised to power equals something else, right? So you can identify A, B, and C and write it in logarithmic form. So go ahead and do that. Okay. Now this process is easy, as long as you remember this rule. And hopefully remember this and how this rule comes from this rule. Okay, but
So.
Okay. Now how are you gonna do log base 4 of 2? Gonna need to use your calculator. Now, actually, you can do that, it's 1/2, but you'll work through the problems and probably understand how I got to 1/2 there. But if you put it into your calculator, okay, here's a rule. Okay. You have a log button on your calculator. You also have a natural log button, LN. You could use either log C over log B or LNC over LNB. Okay. You can use the log button or you can use the LN button, but don't use both buttons on the same calculation. Use one button or the other. And when you do that, you're gonna get 1/2, aren't you? Anybody get 1/2? 1/5? You punch that into your calculator, it'll really tell you to do that. Punch that into your calculator, see if you don't get 1/2. In this case, it would be log 2 divided by log 4. Just divided, log of this divided by log of this. We can say then that x minus 3 is log of 2 over log of 4. You could get x equals 3.5 or 7/2. Okay. So now, a minute ago, you didn't have a clue how to solve an equation like that, except by trial and error. Okay. So let's try another equation. One more is all we have time for. Let's say it's log x squared plus 4. Make that log base 3. X squared plus 4 equals 2. Change the form to exponential form and get a solution. Okay, if you use the rule, we're going to find that x squared plus 4 equals 3 raised to the second power. You want to identify A, B, and C and be careful about it. After a while, you learn how to look at it. Can you solve that problem? Oh yeah, you get x squared plus 4 equals 9. X squared equals 5, so x equals plus or minus the square root of 5. Okay? So it often becomes very easy to solve this formerly incomprehensible equation. So you just learned something important. Okay, practice that. Practice using the logs. Open Math will tell you a little bit more about what they are and the reasons why we do these things, but there's the bottom line. And try to understand the whole idea of exponential functions based on compound interest.